property of Fourier transform which we had introduced yesterday, and we will also close this chapter. So we bid farewell to continuous Fourier transforms today. The modulation property, I said that if I have a product of two functions p of t s t, then the Fourier transform of this is 1 over 2 pi convolution of p omega with s omega. We had proved this relationship and we also tried to illustrate this with the help of an example. And the example that we had chosen was p of t is equal to cosine omega 0 t, or we chose the other way around. It doesn't matter. One of the functions is cosine, which I can write as half of e to the j omega 0 t plus e to the minus j omega 0 t, and therefore its Fourier transform p omega is equal to 2 pi times half delta omega minus omega naught. So it would be pi delta of omega minus omega naught plus pi delta of omega plus omega naught. In other words, it contains two impulses at omega equal to plus omega naught and omega equal to minus omega naught, each of strength pi, and therefore pictorially our p omega versus omega is simply we have a impulse of strength pi at omega 0 and an impulse of strength same strength pi at omega equal to minus omega 0. Now what you have to do is to convolve this with s of omega, and suppose s of omega is a low frequency signal, let's say like this, band limited to omega 1 and minus omega 1, all right, band limited to omega 1. We have also tacitly assumed that omega 1 is less than omega 0. Now if I convolve these two, then what I get is s omega, forget about the multiplying constants, multiplying constant is pi, we will ignore that. S omega, you can reinstate this if you like, s omega star delta omega minus omega naught is simply equal to s of omega minus omega naught. Similarly, s omega convolved with delta omega plus omega naught is simply equal to s of omega plus omega naught. In other words, what we get by convolution of p omega with s of omega are two such triangles centered at plus omega naught and minus omega naught. The result will look like this. If we call this r of omega, which is equal to what was the multiplying constant, 1 by 2 pi s omega convolved with p omega, then what we have is we shall have two triangles like this, centered at plus omega naught and minus omega naught. In other words, the spectrum which was centered at origin, which was a low frequency spectrum as far as capital S omega is concerned, the spectrum which was a low frequency spectrum like the audio spectrum, for example, speech or music, has now been transferred to a higher frequency omega naught, all right. And this is what we mean by modulation, that is, a low frequency is superimposed or used to modulate a higher frequency omega naught, and it is this higher frequency which contains all the information of the low frequency signal. The spectrum is intact means information is intact. This is now suitable for transmission through radio antennas. If you had to transmit the low frequency spectrum through an antenna, you would have to reach heavens. The height of the antenna would have to be extremely large, and it would have posed a civil engineering problem. What one does is one transforms, for example, FM is typically in the range of 107 megahertz. The Delhi transmission is 107 megahertz, whereas the audio band ends at 16 kilohertz, 16 hertz to 16 kilohertz. So 16 kilohertz, this band is superimposed on 107 point something, I don't remember, that frequency for modulation, and then it is transmitted. The other transmission that you get in the medium wave is amplitude modulation transmission, and this is what we are talking of here. That is, multiplying a high frequency signal by a low frequency signal causes an amplitude modulation, and in the frequency domain, this is the picture, this is the spectrum. Suppose you transmit this and then you want to receive it at some point, all right. You transmit this to a distant location, then one wants to recover the audio frequency. A very simple method, there are many methods which you learn in the principles of communication engineering in the third year. Now, a very simple method would be that you simply convolve this, that is, whatever you get here, suppose this is R of t, this is the signal that you receive in a receiving antenna, all right. Then what you do is you multiply R of t by, again, the same high frequency called the carrier, because omega 0 carries on it the low frequency spectrum. So this is called the carrier. You just multiply by the carrier. This is one of the very simple methods. Many alternative methods will be learned later, but one of the simple methods is this. Now, if you multiply this by cosine omega 0 t, in the frequency domain, what you are doing is you are convolving this again with two impulses in the frequency domain, one at omega 0 and the other at minus omega 0, all right. Now, if you convolve this with this as well as this, obviously you shall get two spectra. Similarly, from here you will get convolution of this with this, the impulse at omega 0 and the impulse at minus omega 0. That will also create two such triangles. But interestingly, two of these triangles will be at low frequency. You can see this, that S omega star, I beg your pardon, R omega star delta of omega minus omega naught would be simply R of omega minus omega naught. In other words, this will be shifted to twice omega naught instead of omega naught. This will be shifted to twice omega naught. And the other one would be, if you convolve this, if you convolve R of omega with minus omega naught, then what do you get back? You get back S of omega. Isn't that right? And similarly, if you convolve this triangle with both of these, there shall come another exactly similar spectrum. And therefore, the result of this would be, I am omitting the details of calculation, result of this would be, you get back the original low frequency and you get two other triangles which are centered at 2 omega naught and minus 2 omega naught, and this is centered at 0. The heights shall be different because multiplying constants we have not taken into account. In fact, the height of this will be twice. If this is half, then this would be 1/4. Can you guess why? Two terms are being superimposed on each other, two identical terms, so it becomes double. So if this is 1/4, then this becomes half. And then what do you do? You see, you have got back the original low frequency spectrum, but you also have the high frequency. So what you have to do is to construct a low pass filter. That is a filter which passes low frequencies, let's say 0 to some value omega c, which is greater than omega 1, greater than or equal to. That is, you pass this spectrum through a spectrum window which discards the high frequencies and retains only the low frequencies. And this is what then you amplify in an audio amplifier and power and enhance the power by means of a power amplifier, put it to the stereo and listen to it. This is the process. So modulation is an extremely important property of Fourier transforms, and one should understand this carefully, not only for Fourier transform's sake, but also for later use, that is in communication. Let's look at another example of modulation. R of t equal to P of t S of t. And suppose my my S of t, the signal, is some arbitrary signal like this. Let's say let's say an arbitrary signal like this. This is my P of t versus t, all right. And let us suppose that S of t is a sequence of impulse functions, that is delta t minus kt, where k goes from, let's say, minus infinity to plus infinity. It's a chain of impulse functions. That is, this looks like this. It's a chain of impulse functions. It starts at k equal to 0, then capital T, 2t, and so on and so forth. Now, if I multiply this function by the delta function, well, what actually happens is the following. R of t is equal to summation delta t minus kt multiplied by P of t. What did I assume? I assumed this to be S of t, right, P of t, and therefore I can, since the delta function exists only at t equal to kt, I can write this as summation P of kt multiplied by delta t minus kt, where k goes from minus infinity to plus infinity. Is that okay? Which essentially means that I am sampling out the values of the function P of t at regular intervals of time. In other words, what I am doing is I am converting the given signal P of t, into a discrete time signal. This discrete time signal occurs at regular intervals of time. That is, what we get at the output of this, at the output of the multiplier, is impulses like this at regular intervals of time, whose strengths are equal to the value of P of t at those instants of time. These are 0, capital T, 2t, and so on and so forth. So, what in effect we are doing is, from a given whole, we are sampling the values of the signal. So, this process is called sampling, and the sampling is being done with the help of a chain of impulses, and therefore this is called impulse sampling. As you shall see later, this is the heart of all digital communication. This is the heart of digital signal processing, and we shall have a closer look at sampling a little later. But you see, sampling also is a manifestation of the modulation property of Fourier transforms. Now, what happens? Let's see, if we do this sampling, then what happens in the frequency domain? You see, what we are doing is, we are multiplying R of t. R of t is STPT, where P of t is equal to summation delta t minus kt. K goes from minus infinity to plus infinity. And if we can find out capital P of omega, R of t is STPT. If we can find out capital P of omega, then the spectrum of the resulting signal would be simply 1 over 2 pi P omega convolved with S of omega. All right. Now, P of t is equal to delta t minus kt, k equals minus infinity. I again made a mistake. This is S of t. S of t. I should make a correction here also. This is S of t. Okay? I'm sorry for the mistake. All right. Now, as you see, S of t is a periodic function. It's a regular chain of impulses at regular spacings, regular intervals of time. So, it's a periodic function, and we have already done the Fourier series for this. The Fourier series for this, well, S of t is, what are the coefficients? The coefficients are all 1 by t, coefficients are all 1 by t, and therefore 1 by t e to the j k omega 0 t, k goes from minus infinity to plus infinity. This is the Fourier series where omega 0 is equal to twice pi over t. Alright. This is the Fourier series. We have already done that. We also know that the Fourier transform of e to the j k omega 0 t is simply twice pi delta of omega minus k omega 0. And therefore, if S of t is the chain of impulses that is delta t minus kt, k goes from minus infinity to plus infinity, then capital S of omega is equal to summation, well, 2 pi by t. 2 pi comes from the Fourier transform of e to the j k omega 0 t, delta omega minus k omega 0. K is minus infinity to plus infinity. The interesting thing is that the chain of impulses in the time domain transform into a chain of impulses in the frequency domain. This, if you plot this in the frequency domain, it would be simply a chain of impulses like this. You have an impulse here, and so on. Zero, omega 0, 2 omega 0, 3 omega 0, and so on, minus omega 0, and so on. Okay, so a chain of impulses in the time domain transforms into a chain of impulses in the frequency domain. Now, let us suppose that my signal P of t is some arbitrary signal such that its capital P of omega is band limited. Let's say it is like this. We always take a band limited signal like this. This is a hypothetical signal. It's only for illustration. Suppose P of omega is band limited to omega 1 and minus omega 1. What you have to do now is to convolve this with a chain of impulses in the frequency domain. That is, you have like this, omega 0, 2 omega 0, 0, then minus omega 0, and so on. Obviously, the convolution would be P of omega minus P of omega convolved with delta omega is simply P of omega. P of omega convolved with delta omega minus omega naught would be P of omega minus omega naught, and so on. So, what happens is this spectrum, by convolution with a chain of impulses in the frequency domain, is converted into a periodic function, isn't that right? Which repeats at regular intervals of frequency, and this interval is equal to omega naught. Let us suppose, well, let's draw the picture and see what happens. A picture, therefore, shall be like this. What we are plotting is R of omega, which is the convolution of P omega with S omega, and of course there is a factor of 1 by 2 pi. Let's ignore the multiplying factors. The shape of the spectrum shall therefore be something like this. This is 1, then the next triangle, then the next triangle, and so on. It repeats at regular intervals of time, and the ordinates are, this is 0, this would be omega naught, this would be 2 omega naught, and so on. Please remember, omega naught is 2 pi divided by t, where capital T was the distance between two impulses in the time domain for the signal S of t. All right. Now, this is omega 1 and this is omega 1. All right. And what is this frequency? Omega naught minus omega 1. All right. Now, you have to consider two situations. One is, if these two triangles superimpose on each other, then obviously the shape of the spectrum changes. Shape of the spectrum changes. For example, if this superimpose like this, alright, then the shape of the spectrum would be something like this. Alright, it will have triangles on the top, but it will have flat portions. On the other hand, if these two do not superimpose on each other, then the shape of the original spectrum of P of omega is retained, and if necessary you can recover this spectrum by means of a low pass filter, that is a filter which passes only, let us say, this block of frequencies and cuts off the rest. In a sense, what we have discussed now through this modulation is the so called sampling theorem. The sampling theorem says that if you sample a continuous time signal, then all information of the signal is contained in the sample signal, all information is contained in the sample signal, provided the end of this spectrum does not overlap with the next spectrum. What will be the condition for this? Omega 0 minus omega 1 must be greater than omega 1. That is, omega 0 should be greater than twice omega 1. And what is omega 0? Omega 0 is the sampling frequency. The sampling interval was capital T, so 2 pi by T is the sampling frequency in radians per second. The sampling frequency therefore must be greater than twice the highest frequency content. Omega 1 is the highest frequency content of the signal, and this is the statement of the famous sampling theorem due to Nyquist, N-Y-Q-U-I-S-T, Nyquist. Nyquist stated that if you sample a given continuous time signal at a frequency which is at least twice the highest frequency content of the signal, then the spectrum of the signal remains intact or undistorted. The only thing that happens is that it becomes repetitive, it becomes periodic. However, you can extract the signal back if you pass it through a low pass filter like this. You shall be taught sampling theorem, at least the statement once again in this course. Later when you do sampling, you will be asked to recall in the course on digital signal processing. If you take that course, you will be asked to recall this in your principles of communication, you will be asked to recall this in digital communication. There are a number of and also in digital control, where sampling is a must. Wherever sampling is important, one must remember that the sampling rate must be at least twice the highest frequency content of the given signal, at least. There can be an equality sign also. We usually avoid an equality sign. Okay, can you guess why? Because filtration would be difficult. Not only that, there is no practical signal which is band limited. In other words, actual signals would be something like this, So if this edge coincides with this edge, it means that there will be substantial distortion. Well, one of the things is that because no practical signal is band limited, distortion is a must. You cannot avoid this. The only thing you can do is to keep it to as low a value as possible. Alright. So what one usually does is, since no practical signal is band limited, for example the telephone signal, the audio signal in the telephone, if it is to be transmitted by digital telephony, digital communication, then you must band limit the signal. 16 kilohertz is too high, so one band limits to 3.3, that is the standard rate. Telephone message transmitted by digital telephony, which is most of the case now, digital telephony is band limited to 3.3 kilohertz and is sampled at the rate of the lowest rate that you need is 6.6, but it is kept at 8 kilohertz. That is the standard value for sampling an audio signal to be transmitted by digital telephony, 8 kilohertz. So that there is a safety margin of how much? 1.4 kilohertz. Okay, this safety margin is allowed so that the trailing end becomes negligible. In other words, you can approximate this by means of a triangle. All right. So this is why omega 0 is usually kept greater than 2 omega 1, not exactly 2 omega 1. In theory, this is possible, but in practice, since no signal is band limited, therefore it is required that there be what is called a guard band. This band of frequencies from omega 1 to omega 0 minus omega 1 is called the guard band. It guards against the distortion that might occur if omega 1 was exactly equal to omega 0 minus omega 1. But if you are not too careful about your system design, you may ignore Nyquist's band or Nyquist restriction. If you do, then obviously your spectrum shall be distorted, and there is no way that you can recover the original spectrum or the original signal or the message from the transmitted sampled version of the message. And the distortion that arises is known by the name of aliasing distortion. You shall learn more about this later. But as far as the theory is concerned, do not ask for the theory again. It shall not be done. You will simply be referred to as the sampling theorem, and the sampling theorem is not obeyed, then it's called aliasing distortion. And the meaning of the word aliasing means that high frequencies pose as low frequencies and low frequencies pose as high frequencies. So it is called aliasing distortion. Finally, before we bid farewell to the topic of Fourier transforms, well, we would like to work out a number of examples in the time that is left, and emphasizing the concept of frequency response. I told you yesterday that the frequency response h of omega is the Fourier transform of h of t, and therefore h of omega is as good a characterization of a linear time invariant system as good a characterization as h of t. All right. If x of t is given, h of t is given, then y of omega is equal to x of omega, h of omega, and therefore y of t can be obtained as the Fourier transform of capital Y of omega. This we discussed yesterday. Now, basing on this, we shall work out a number of interesting examples. One is, first of all, the most general situation is that you have AK for a continuous time system, dkyt, dtk, k equals 0 to, let's say, capital N, is equal to the most general characterization of an LTI continuous time system is k equal to 0 to m bk dk x of t dtk. And in the last tutorial class you have seen what happens if m is greater than or equal to n. There are complications. Delta functions are introduced. You will see that if you take Fourier transform, then the considerations are much simplified as compared to working solely in the time domain. The first thing we notice is that h of omega, the frequency response, can be very simply written by inspection. If you take the Fourier transform of both sides, and if you remember that dy dt transforms as j omega times capital Y of omega, then you simply see that what we shall have is a polynomial in the numerator and a polynomial in the denominator, and this polynomial would be ak j omega to the power k, where k goes from 0 to capital N, and this would go from 0 to capital M bk j omega to the power k. Is this clear? Is this obvious? It's not obvious. All right. Let's take an example. Non-trivial one. Let's say y2 dot plus 6y dot plus 9y. We shall come back to this example later. x2 dot plus 3x dot plus 2x. Let's consider an example of a differential continuous time system. Now you see, if you take the Fourier transform of both sides, of course we assume initial rest. If you take the Fourier transform of both sides and you say that y of t transforms to capital Y of omega and x of t transforms to capital X of omega, then you know that y of omega should be equal to capital H of omega multiplied by x of omega. Alright. Capital H of omega is the frequency response, which is the Fourier transform of the impulse response. So which means that the frequency response can be obtained by taking the ratio of y of omega to x of omega. Alright. This is what we are doing here. Take the Fourier transform of both sides. Then we get j omega squared capital Y for the first term. For the second term, 6 j omega y capital Y plus 9 capital Y is equal to j omega squared capital X plus 3 j omega times capital X plus 2 capital X. Alright. Is there any question on this? We have used the property that d dt of x of t, this transforms as j omega capital X of omega. This we have proved already. Alright. Can you go ahead? Okay. And therefore, if you take the ratio of y to y of omega to x of omega, which by definition is h of omega, what you simply get is the following. You get j omega squared plus 6 j omega plus 9, and in the numerator you get j omega squared plus 3 j omega plus 2. Alright. It is conventional, instead of writing j omega every time, it is conventional to write this as s squared plus 3s plus 2 divided by s squared plus 6s plus 9 under the condition s equal to j omega. So you see, the frequency response function h of omega can be written down by inspection. In general, if I have summation ak dky dtk equal to summation bk dkx dtk, if this is the general equation of the linear time invariant system, then obviously h of omega is what I wrote earlier, that is summation ak s to the k summation bk s to the k under the condition s equal to j omega. Is this clear now? For a general system, we can obtain the frequency response function by inspection. Let's take some simpler examples. We have y dot plus ay equal to x. Let's say you consider an LTI system which is like this. Then if I take what is h of omega? By inspection, 1 divided by, the coefficient is 1 divided by s plus a under the condition s equal to j omega. Alright. And because h of t is the Fourier pair of capital H of omega, the finding of impulse response now is simply amounts to inverting h of omega, and we already know what the inversion of h of omega is. It is e to the minus at u of t. This is a much simpler method of finding the unit impulse response of a linear time invariant continuous time system. Let's take another example. Slightly more complicated. y2 dot plus 2y dot plus y equal to x dot plus 2x. Alright. I want to find the impulse response of this. In the tutorial class, we told you that what you do is you first find out the unit impulse response of the system when the right hand side is replaced by x, and then apply the principle of superposition. You can do that, or you can also do it like this. if you want to work in the frequency domain alone, if you want to work in the time domain alone, that is the best method. That is, replace the right hand side by x and then apply the principle of superposition. If you want to work in the frequency domain, then this is a much simpler method, because your frequency response function now becomes s plus 2. I am writing by inspection, s from this first differentiation plus 2 divided by s squared plus 2s plus 1 with s equal to j omega. Alright. Now this is s plus 2 divided by s plus 1 whole squared under the condition s equal to j omega. I do not know the inverse transform of this. What I know is the inverse transform of 1 by s plus 1. I know the inverse transform of 1 by s plus 1 whole squared. The function shall be multiplied by t, alright, or 1 by s plus 1 whole cubed. I know that too. The function shall be multiplied by t squared, and so on. So the first thing that we do is to expand this in those kind of forms. That is, I write a by s plus 1 plus b by s plus 1 whole squared. I don't want anything else than a constant in the numerator. How do you find a and b? Pardon me? Both are 1 here. But how do you find it in general? What you do is you write the numerator of this and equate to s plus 2. Then you find out a and b by equating coefficients of like powers of s. And the result is, in this case both are 1, and therefore, is that right? S plus 1 whole squared. Yes, you are right. Under the condition s equal to j omega. This is h of omega, and therefore now I can invert term by term. For this it would be e to the minus t ut, and for this it would be t e to the minus t ut. So that's the final result for the impulse response. We conclude this lecture by working out an interesting problem from the text. 436. 436 says, part A, it's a fairly long problem, but a very interesting one and simple too. 436A says there are two systems, h of t and g of t, which are cascaded. That is, one comes after the other, alright, h of t, g of t, and it is said that h of t and g of t are inverses of each other. They are inverse systems. That is, if you invert h of t, you get g of t. Not Fourier inverse. It is the inverse system. Now, inverse system means that if this is x of t, then the output should be x of t. Alright. So, the question is, what is the relationship between h of omega, that is the Fourier transform h of t, and g of omega? Obviously, the product should be equal to? Should be equal to? No, it should be 1. Because what you are doing here is ht convolved to gt, and this becomes a product in the frequency domain. And therefore, all that you get is h omega multiplied by g omega equal to 1. This is the answer to the first question. Second part, is this understood? No. Okay. Let's go to the frequency domain. Capital X of omega. You have h of omega. You have g of omega. We go to the frequency domain, and then this is x of omega. Now, how is this possible unless this product is equal to 1? Alright. In the time domain, it is ht star g of t, and the frequency domain is the multiplication of the two. So, the multiplication is equal to 1. Is it okay? Alright. Now, we are going to more complicated problems. We have a linear time invariant system, part B, LTI system, whose frequency response is of this form. It is 1 for 2 less than mod omega less than 3 and 0 otherwise. Alright? Which means that if I plot it, it looks like this. Okay, this is my h of omega. This is 2 and 3, minus 2 and minus 3, and here it is 1, the value is 1. This is my h of omega, the frequency response. The question is it possible to find an input x of t such that, follow the question carefully, such that the output is of this shape, y of t is a triangle like this, 1 and 1. Is the question clear? It's a bit unconventional question. Let me repeat the question. Question is, you are given a linear time invariant system to which you apply an x of t and the output is y of t. The system is characterized by, not by its impulse response, but by its frequency response, and I told you the frequency response is as good a description of an LTI system as the impulse response. So this should be good enough. H of omega is 1 for a band of frequencies 2 to 3 and it's 0 otherwise. Question is, can you find an x of t such that y of t is of this form? Y of t is simply a triangle like this. This is the question. If you can find one. If not, say why you cannot find. That is the question. All right. Now, the solution of this in terms of Fourier transforms is like this. Your y of omega is equal to x of omega times h of omega. All right. And let's take a particular frequency, let's say 0, DC. You have to think about such problems a little bit before you come to a solution, but it's extremely simple really. Y of 0, just one spot frequency. You see, if it is possible, then one example is not sufficient. But if it is impossible, one example, one counter example is. So we are trying to construct a counter example. Let us see if it works. Y of 0 is x of 0, h of 0. Now what is h of 0? 0, and therefore this is equal to 0. Now required y of t is this, 1, 1. So one method would be calculate the Fourier transform on this and see if at DC, if at omega equal to 0, the value is 0 or not. But you see, calculation of y of 0 does not require the computation of the Fourier transform. Why not? Because capital Y omega by definition, now follow this carefully, it is yt e to the minus j omega t dt. Yes. Can you go back? Okay. The calculation of y of 0 does not require the computation of y of omega totally, because if you look at the definition, y of 0 is simply minus infinity to infinity y of t dt. That is the area under the curve. What is the area? Half. Now what is the answer then? Not possible, because y of 0 is 0 and y of 0 here is half, and therefore the answer is, it is impossible to find an input for which the output shall be of this form. The next part of the problem B2, the same problem, that is h of omega is band limited, that is 1 for omega between 2 and 3 and it is 0 otherwise. Question is it possible to to design an inverse system of this? Is it possible to design a system which is inverse to this system? Answer?
No, sir.
No, because the inverse system should have a frequency response which is 1 by h omega, and 1 by h omega is not defined outside this range 2 and 3, and therefore the answer is no. No inverse system can be found out. Part C. Part C concerns a practical problem, an auditorium in which music is being recorded, and this recording shall be sold in the market, but the auditorium unfortunately is a poor auditorium. In other words, there are echoes. All right, an auditorium has echoes, and so if there's an impulse of sound at some instant of time, it repeats after regular intervals. All right, so what you get is delta t is the input, then it's added to, let's say, delta t minus t with some attenuation alpha, because the sound, let's say, goes to the walls and then gets reflected, some attenuation alpha, then it gets alpha squared delta t minus 2t, and so on and so forth. And therefore, if alpha is not sufficiently large or sufficiently small? Sufficiently small, the music that you record is a distorted version of what was actually played, what was actually sung by the singer. And therefore, such recording, if you want to make a gramophone record out of it, or a video or a cassette out of it, well, nobody is going to buy this because it's very noisy. So what people have to do, on the other hand, in public auditoriums, let's say Sri Ram Bharatiya Kala Kendra or even our seminar hall, one cannot ensure that there is no echo. So if you want, let's say, Ali Akbar to play here and his music to be recorded and sold in the market, well, the gramophone companies, what they have to do is to process this signal such that the echoes are removed. All right, it's a question concerning that. Now, what is given is that the auditorium's impulse response, h of t, is given by summation k equal to 0 to infinity e to the minus kt delta t minus kt. In other words, the attenuation is e to the minus t. One time attenuation is e to the minus t. All right. What one wants is, if this recorded music is to be made distortion free, what is the processing that is needed? All right. Obviously, the concept of inverse systems can now be brought in. All right. What we do is, this is our signal. What the singer sings, and then you have the auditorium whose impulse response is h of t. It is not simply a delta t, but it's a continuation of echoes. And then the processing that you need is, you need another LTI system having the impulse response g of t such that at the output you get x of t, and therefore g of t and h of t should be inverses of each other. Now, if you consider h of t, which is summation infinity k equals 0 e to the minus kt delta t minus kt, you notice that its h of omega, is simply, yes, what would it be? Well, if you expand this, it is delta t plus delta t minus t plus etc. to infinity. So if you take h of omega, then you get 1 plus e to the minus j omega t plus etc. to infinity. And therefore, h of omega would be simply 1 by 1 minus no, I made a mistake, e to the minus t, that should be introduced. All right. So it would be e to the minus t and so on. Now if you if you sum up this is a geometric series, you get e to the minus 1 plus j omega times capital T. I'm sorry, let me write this in big. H of omega becomes 1 by 1 minus e to the minus 1 plus j omega times T. So, in order to recover the original music, all that you have to do is to design an inverse system whose g omega is given by 1 minus e to the minus 1 plus j omega t. And if you take the inverse Fourier transform, what kind of impulse response do you want? You want an impulse response which is equal to, yes? For the first term, for unity, what is the inverse? Delta t minus e to the minus t, I beg your pardon, j omega is here. E to the minus t, then e to the minus j omega. What is the inverse Fourier transform? Delta of t minus 1. No, capital T. E to the minus j omega capital T, so delta of t minus t. This is the impulse response that you want. Alright? And it's not impossible to design a system which has an impulse response like this. And this is why the dumb phone companies are in existence in the market, because they cannot guarantee that the studio would be eco-free. And if it is an open auditorium, yes, you can almost guarantee. Not in the open air theatre that you have in IIT. It has a lot of reflections and so on. Alright, this is, with this we bid farewell to the topic of Fourier transform. Next time, Fourier transform for continuous time system. Next time we take up discrete time system.